Hello, everyone, and welcome to this breakout. We are going to cover here in this first session the poster that you are seeing now, and I'll announce a poster presenter, and then a session on similarity search and text mining in some way. So the first is the poster, and for the poster we have here Jaccard, who will be presenting the poster that he has created and presented yesterday as well. This is about monsters and mice. You have 5 minutes for the poster, and then we get with the presentation.
Okay, thank you, Flavio. So my name is Jaccard. I'm a fourth-year PhD student from NC State University. I work with Dr. Menzies. Our lab has been collaborating with LexisNexis for years, and this year we want to demonstrate the power of big data on the core business value problems. So this is why we chose the topic which we thought will attract most interest, where to invest your money. But based on the number of people in this room, this might not be the most attractive topic. So anyway, to start with, we collect data from this sector government public website. Okay. What we do is that we try to extract information from the 10K filings these U.S. public companies need to file every year, and we target as the name of board of directors, and by trying to do this, we first applied name entity recognition tools, but our results suggest that this like existing standard toolkit like Stanford toolkits, they do not perform very well. They like outputs very low precision, which means we have a huge number of false positives. So we switched to another algorithm. So we curated our own rule-based algorithm, and we had to do a lot of work to generate several rules to handle the edge cases. But finally, we achieved a good result. Like we can extract about 99% of all these board of director names, and with almost 100% precision based on our manual check. So after we have the board of directors extracted for every US public company, we can construct a social networking graph for all these companies. By doing this, what I mean is that if person A is on board of director of company B and also company C, then company B and C are connected by this person A. So there is so we are treating these U.S. companies as nodes in the graph, and the persons which connecting these companies as edges. And we end up with a huge social networking graph, which consisting of like 7,000 public companies and 38,000 of these board of directors. One thing we found that surprises us is that there is only one huge connected component in this social networking graph, which consists like 40% of the public companies, and all the rest 60% companies, they are mostly like isolated. They do not. This company does not connect to any other companies, or they connect to like one or two companies which basically owned by the same person. So one thing that occurs to us is that what's the difference between these connected 40% of companies or over the isolated 60% of the company? So we name these connected companies as the monsters because they are like powerfully connecting together, and those isolated companies as mice. Our hypothesis is that the board of directors which are on board of these monster companies, they have more insights of the industry, the business, and they know where to put their money on. So we think these monster companies might be more successful. But when we try to validate our hypothesis, we use this US Fortune 500 company data, because we do not have all the revenue data for all the 7,000 companies. We only use the Fortune 500 data. And what we found that among these US Fortune 500 companies, 70% comes from these monster companies. So maybe monster companies can have more opportunity to grow themselves to the Fortune 500. But a contradictory finding is that these among these 500 Fortune 500 companies, in average, the mass companies have more revenue than the monster company, like showing in this histogram. Like in every percentile, like these mass companies has about 20% higher revenues, and for the 90th percentile is about like 12 billions worth in revenue. So there also might be conclude that monster cannot focus as well as mass on the small details. And maybe if you want to pick a company to invest, pick the Fortune 500 companies which are isolated might be a better idea. Yeah, thank you.
That was a very good presentation. Thank you very much. And this gives me a good idea now. If you have been investing in your Russell 1000 or Dow or NASDAQ indices, well, wait. There will be a share index very soon, and you heard it here first. Remember that. Anyway, now we need to welcome Fabian. Fabian Fier has been a collaborator and a community member in HPCC for a very long time. He's done a lot of work around similarity search, and he's been a presenter in previous HPC summits as well. So without more preamble, let's get Fabian and his presentation now.
Thank you, Flavio. So I hope you can hear me. I want to talk about set-similarity, join, and search. So I'll start with the join, and we come to the search later with different prefix schemes, and we will come to these details as well. So let's first get started. Where do I come from? I come from Berlin in Germany. This is my university, Humboldt University, and we have a joint research project together with Elsevier. So this is the link to LexisNexis. Both of these companies are part of Read Elsevier, and this is why I'm here. This project is called the HEAD Center, so it's the Humboldt Elsevier Advanced Data and Text Center. One part of this research project is research integrity. So we look at the spectrum of things that you may do in research and which are not acceptable anymore because there's a lot of colors between black and white. And the other part is how to support this technically, and this is where I'm part of. So when you think about plagiarism detection, this is quite an important task, and we can support with technology. So what's the motivation of my work here? So I already named it, plagiarism detection. So when you think about people who, for example, copy texts from other texts and use it as their own, we can obviously do this by technology. We can use that to find plagiarism. Maybe community mining in social networks is also relevant. So when you think about you want to find communities of people who share similar attributes, you want to find that. Near duplicate web page detection is interesting when you have a search engine. You don't want to index the same data many times to save space or have better results in the end. Document clustering would be an example, and many others. So one problem of this is when you have large data sets, this is quite an expensive operation, at least the join. So the solution is parallelism. We are here at the HPCC conference, so HPCC is a parallel system which we used here for that, and one algorithmic approach is a set-similarity join. So I will talk about the set-similarity join here. There will be, of course, other approaches are also there. So this is the agenda here. At first I want to go to the problem statement, talk about a common approach which is called the filter and verification approach. This is the main work here, the parallel set-similarity join algorithm. And there are two extensions. The first extension is sliding window set-similarity join. This is actually what makes it usable for plagiarism detection, and set-similarity search. So join and search are very close. And we can use the ideas of the join to make search possible as well. In the end, I want to show you the experimental results, which are quite interesting and nice. So first of all, data representation. Every record, which are also referred to as a document, is a set of tokens, and each token represents one word. You can have other representations, think of vectors or multisets. We use sets here. Our input is a set of records, a similarity function, and a similarity threshold. So a user can choose a similarity threshold and say, from this threshold on, I consider two records being similar. So our output of a similarity join would be all pairs of records where the similarity is above the user-chosen threshold T. How could we compute this? Let's first look at an example. We have a similarity function we use the Jaccard similarity function. There are other similarity functions as well. We use this here just as an example. So we have three input records, R1, R2, and R3, and each of them has several tokens. For example, R1 has A, B, C, D, E. And Jaccard similarity computes itself by this formula here. And the user chose the threshold of 0.8. So when we compare R1 and R2, we get a similarity of 4 divided by 6, which is less than 0.8, so these two records are not similar. Similarly, we can compare R1 and R3, which are not similar, and we can compare R2 and R3, and finally, this is 4/5 here, we get 0.8, so they are similar to our threshold here. Okay, how can we calculate that efficiently? Well, the naive solution would be to calculate the similarity for each pair in our data set. Who has done that before on a distributed system to do a cross join? That explodes quite fast. The computation time will increase very fast, or even we will run out of memory. So this is a very expensive thing here. We can do better. One approach to do it better is the filter and verification approach. In the filter step, we prune all pairs that cannot be similar. So the filter step gives us pairs of records. It's a superset of the result set. We do not lose anything, but it's way smaller than the cross product. In the verification step, we look at all these pairs. These are our candidate pairs, and we verify if they meet our similarity threshold. Common filter techniques are, for example, the prefix filtering. I don't want to go into a big detail here, but we can use just a prefix of records. We just look at a certain part of it, and if this prefix here contains the same token, or if a prefix of another record contains the same token, we can assume they could potentially be similar. If there's no common token, we can be sure they cannot be similar.
Do you want to do questions at the end? Or?
Well, I think maybe at the end, because then we can go with the microphone. Mm-hmm. So this is one filter we can use. Another filter would be the length filter. We can derive from the length, if this length is very different between two records, we can say, okay, they cannot be similar anymore. This is a simple computation we can do here. There are other filters. I don't go into details here, just to let you know some examples. So now I'm coming to our general approach here. Let's assume some input records, R1 to R3 here, R4. And so we first build an index. This index I always marked blue here. So what we index here are the prefixes. So as you can see, for example, R1 is contained twice in this index here. So we have the B is indexed here and the C is indexed. So the prefix of R1 was just B and C. And similarly, R2 and R3 you find in here and R4. And then we probe all these records here against our index. I did this here as an example with R1. And so we probe it's a different prefix. It's a little bit longer. It contains B, C, and D. I don't want to go into detail. We probe this, so we get the lists of these 3 tokens here. And we can say for our probe record R1, we get R2 and R3 and R4 as candidates. So what do we have to do with our candidates? This is a superset of the result set, so we have to verify it. So we look at these token sets and compute the set similarity function we chose, and we get one similar pair here. So our goal is to implement this approach as a parallel algorithm. We already did that before, so this is nothing very new, but we experiment with different prefix schemas. So up to now in the research, only a prefix schema of 1 was used typically, which means the overlap in the prefixes has to be 1, so that you can say like they could be potentially similar. But it's also possible to use larger prefix schemas. You could, for example, use 2. What happens if you use 2? So if you add 1 to the prefix schema, you also add 1 to the prefix size, and we also add 1 to the needed overlap. So our index becomes a bit bigger. So as you can see, R1 here appears with D as well, so this prefix here became longer. We also have some more entries here, and when we probe, we also get some more data here. But the amount of candidates becomes less. Okay, so we have here a trade-off between the size of the index and the candidates we get here, but we still get the same result. And then we extend our idea to set similarity search and a sliding Windows set similarity join. Okay, so idea of the parallel algorithm. On a high level, I will present this as a concept and then on ECL level. So first of all, we need to do some pre-processing. We need to order the token sets by global token frequency. So this is the hello world example of all distributed systems, a word count, and then we sort the tokens by their frequency. The idea is to have the least frequent tokens in the prefix so that we do not get too many candidate pairs. Then we build the inverted index on the prefixes. So here we have our input records, and here we see our index. And what do we do with it? We calculate our so-called pre-candidates. So we apply the first filter here. We take again our input records. We compute the prefixes from this input, and we join it with the index we created before. Our first filter here is the left record ID has to be smaller than the right record ID. That has a practical reason, because we already know that if the record ID is equal, it's not interesting, they are the same, and we do not want to create double results. So if R1 is similar to R2, it's also vice versa. So we just need one of these pairs. Okay, and then we get our result here by simply creating the cross product here within the lists we get from this join here, and we can throw out such record pairs which do not meet the length filter at this stage here. What's the problem in this graph here yet? When I'm talking about the length filter, I didn't show this for brevity, so the index contains more information than just the record IDs. We also apply we also save the length here so that we can apply these filters. Then we filter the pre-candidates by their overlap. So this is now what is also different compared to before. We have several pairs which have an overlap of 1, and we can say these cannot be similar. So we can throw these out. These are not candidates, and then we compute the similar pairs out, or we can verify which pairs are similar in the end. Okay, so how did we implement that? This is the pre-processing, so this is quite straightforward. We take this, so this is for the global token order. So we just count the occurrences of the tokens. So we normalize each record, and we aggregate it with a table, and we sort them by the frequencies. We apply a little trick here. We project each token to a new internal token ID. That makes life easier because we we can create an order which is exactly the token order in the end. So it's always 1, 2, 3, 4, 5 in the end. So and we reorder the token set of each record based on this token order with project. Yeah. So then we build the inverted index. So we extract the tokens, their position and their length. The position we need for another filter, don't worry about it. And we again use normalize for that. So now we get this prefix here for this record, which is B, C, and D. And we know its position here, we know the length of the record, and we know which record it came from. And then we calculate the pre-candidates. So again, we go through our records here. This is a slightly longer prefix we need, and we again use normalize for that, and we get our tokens here. In addition, we also save the minimal record length that can be similar to them. So this is for the length filter in the end. To accelerate the join of these tuples, we don't store the token sets in the tuples, so we found out it's way better to do the join in the end from the original data set and not take the complete data in this process here, because we would have to copy it, obviously. So here we do this join that I was talking about before. So we have our index and we have our prefix list here, and we simply do the join and we apply our filters here. So we have the length filter here, we have this RID filter here, and so we get our list of candidates here, and quite straightforward in ECL. Then we filter the pre-candidates. So we count the overlap of each pair with distribute, sort, and rollup, and we skip all pairs which do not pass the position filter. So the position filter is one of the filters. It's a little bit complicated, and so we implemented it in C++ here. So here we see we have an overlap of 3 for this pair here, so this would survive the filter, and here we have an overlap of 1, so our filter throws out this pair. Last but not least, we compute the similarities of all pairs, so we have to join the original records to it. So we have to do this in a 2-step process. One is join the left one, and then we join the right one. And by doing this, we also do the verification. Okay, so this was the first part. This was the set similarity joins with different prefix schemes. And now I come to an extension of that, which means sliding window set similarity joins. So when you think of plagiarism, people don't plagiarize whole texts usually, they plagiarize parts of them. So in order to make this work, we look at windows of texts, for example. So here, when this is a record, we simply look at windows within this record. We used fixed size length here, and you can move these windows in a certain way by one word or more. We used more for efficiency. And then we can simply do the same thing that we did before. We can run our set similarity join between these windows here. With the pre-processing here, it basically works like before, but of course we have to keep the order of the records in the beginning, because we cannot move around the tokens before we haven't created the windows. And the join also works like before, except that we cannot use the length filter, which is obvious because our windows are all of the same length. Okay, this was the sliding window similarity join. Now we come to the search. How does this apply to search? So given a search document, you want to find if in your already indexed data set there is a similar one. So we have our records here. We have a query record S, and we want to have all similar, well, I called it pairs here, but we want to have all records here which are similar to our search record. So we want to prepare an index, and we want to query it in a second step. The index creation is done with Thor here. So we calculate the token order as before, and we create two indexes. One index, or both of the indexes, use a payload. So one index is for the token ID rewrite here. As I said before, we had this little trick to rewrite tokens to make them easily orderable by inverse token frequency. And this is our inverted index here. We also save the length here to be able to apply the length filter. And then we can search this with Roxy. So we pre-process the query record the same way. We change the token IDs to our internal token IDs and sort them. And then we do the same thing like before. We calculate the pre-candidates, verify them, and we can use an index join on this to get our results. So now let's come to our experimental results. We used many different data sets. These are all real-world data sets, very small ones here. This is what I used for my research up to now. And we also got some patent data sets. So you can see it starts from 250 megabytes up to 16.5 gigabytes. And when you think about a cross-join on this data, that wouldn't be possible on any cluster I know. We did this on a cluster of 6 Thor nodes, which is, of course, not so big. We have 3 Thor slaves per node. Yeah. Okay, so first result. The prefix scheme has a big influence on the runtime. So here we see a not so nice result. This is DBAP. This was one of the smallest data sets. You see here the prefix scheme of 1, and this is the runtime here in seconds. And you can see the higher the scheme gets, the more runtime we have here. So from this data set, we don't profit from this prefix idea at all. But when you look at this data set, it looks completely different. So this is the Netflix data set. And we start from runtimes of 6,000 seconds here, for example, for a prefix scheme of 1. And when we take a prefix scheme of 2, we are already below 3,000. And it goes even further. So with a prefix scheme of 3, we get something here between 1,000 and 2,000. And with 4, it goes up again. So we have a sweet spot here at 3. Or for other similarity thresholds here, it's it's maybe 2. So something between 2 and 3 is optimal here. So as we can see, it's good to look at the prefix scheme. This can optimize the runtime quite a bit. When does it help? So for short prefixes and many rare tokens, as we have in this data set here, it doesn't help. So there we just take, as we did before this, the one prefix scheme. And when we have long prefixes and few rare tokens, then we take the large prefix schemes. Result 2, the distributed set similarity join algorithm serves well for the sliding set similarity join. So here we see we have the patent data, and we used a window size of 100. And here we also see for a prefix scheme of 1 quite high runtimes, and the runtimes go lower when with larger prefix schemes here, and go up again when we from a certain point. So it works well for this idea as well. And here, just as a side note, when we decrease the window size, then we get slightly higher runtimes, which is not very surprising. We also get more windows. Result 3, the distributed set similarity join algorithm serves well for the sliding window search. So who sees the error in this picture here? We are talking about search. This is the runtime here in seconds. So this is quite high with 400 seconds, so it's milliseconds. So we have an average runtime of these queries here of 0.5 seconds, which is quite nice. So it's quite reactive, and for a distributed system, it's very performant. So I was very happy with this result. Even on the bigger data sets here, which performed not very well on the join, for example, we get very nice runtimes. Yeah, that's it. Do you have some questions?
Don't you have to judge the effectiveness? Oh, it's a microphone. Is it complete to assess your thing on runtimes, or don't you have to judge it on the effectiveness of the join? Aren't your joins heuristic? I couldn't see a completeness guarantee.
The join result is always the same. So it's completely deterministic. There's no variance in the results.
But you've got some magic numbers, like on slide 8. You've got when you're computing your prefix strings, you've got a decision on how many. Like, have you sorted the token? Have you sorted the tokens?
Yes, they are pre-sorted by frequency. I didn't show this magic here because it's a reasoning about sets and the similarity threshold and the similarity function.
Any other questions? Very good. Thank you very much.
Thank you.
Thank you, Fabian. This is very good. I really like the talk. It's a good extension to the previous talks as well. So it's a good addition. So now for the live audience, we'll do a brief 10 minutes interval, and we will please rejoin that live stream in 10 minutes. We'll go to the next session, another poster and another session. For those in the room, also thank you very much for coming. And we have a break of 10 minutes, and then we will start in whatever other session you signed up for. Thank you.
Test, test, test.
Strangers in the night.
It could be that. Just turn it on first. Then you can sing all day long.
Where's it on? Oh, there it is.
3 seconds.
Strangers in the night.
There we go.
Love the Beta 58A.
Oh, yeah.
No, that's a 58. The Beta 58 is too high quality for that. It's just regular 58, yes.
57.
Yeah, I got a 57 that's my spare.
Right. Absolutely.
See, you're doing karaoke tomorrow.
I don't do
Yeah,
karaoke.
you're gonna do Strangers in the Night. You lie. You're gonna do Strangers in the Night. What's that?
Phonetics.
Oh, yeah, very cool. You don't have enough stickers on your laptop.
I need a few more.
Oh, well, I have some for you then. I'll give them to you. Did you get the newer ones? Yeah. You can't take them off, but the thing will fall apart.
It's good thing that we have that projection.
Hello, hello. Okay, we're live and live streaming with everybody that's in the room and everybody that's live streaming. My name is Richard Taylor. We're introducing Jim DeFabia's documentation translation breakout session. We are meant to be starting with Robert Kennedy and his 5-minute overview of deep distributed learning with TensorFlow. However, Robert was able to get an earlier flight. He caught an earlier flight. So instead of the 5-minute overview, I suggest everybody go out to the YouTube and see his 20-minute main stage presentation on exactly the same topic. So without further ado, let me introduce Jim DeFabia. I've known Jim for 25 plus odd years, and we have been working together ever since through 4 different companies. Jim's a great guy, and he knows everything about documentation. Jim DeFabia.
Start over.
So, okay. So we're going to talk about internationalization. So why do we want to internationalize? Out of the world's population, only about 20% are English speaking. From our portal visitors, it's even more English centric. About half of our audience speaks English and the other half doesn't. But if we support more languages, we might attract more people from around the world. And you'll see here a version of our portal that has been translated into Mandarin Chinese. And if you were in China going to HPCsystems.com, this is what you would actually see. So we don't want to lose half of our audience. You know, we really don't want to lose half of our audience. And people that know me know I don't like to give up half of anything. So how would we internationalize? Well, we could get a Babel fish if we were to go back to Hitchhiker's Guide from the Galaxy, but that really doesn't exist, so we have to do it in more traditional ways. Now, in 2013, Comrise, which is one of the HPCC Systems partners, gave us a wonderful gift. They translated several of our manuals into Mandarin Chinese. The ECL Programmer's Guide, version 4.2.03, is still available on the portal. The other books were incorporated into our online training. Well, that was great. Thank you very much, Comrise. It looks really great. I don't understand it, but it looks really good, and I'm told that it was brilliant. But it was a one-off translation. It was nice to have, but it's static. It's a version 4.2, and as you know, we're very close to releasing version 7.0. It wasn't very easily maintainable, the translation, and it's now become outdated. If we were to translate it again, we would have to basically just start from scratch. So what should we do? Well, use the source, Luke. Fortunately, all of our documentation is in XML format, which is a text-based format. So it's very easy to compare differences. We can use git diff right on the GitHub portal. You can see differences, and there are other tools like Beyond Compare and other file comparison tools that compare text quite easily. So we can find the updates to documentation, and once we do the translation once, in the future, all we have to do is translate the deltas, just the changes, keeps the costs low, and makes it a lot easier. So minor differences, in fact, what we'll be doing in-house. And if we add a book, like we had a couple 100-page book, that'll get sent off to a translation company. So open source to the rescue, because we want to keep it simple. So like I said, we set a checkpoint, then we translate that, and later we only translate the differences, just the deltas, And by translating only the delta, the translation costs are dramatically reduced. Now here is an example of a Git diff in the GitHub repository. This is one topic. It's and we've just added a couple of lines. There's just one parameter was added to this function, and it's the rename logical file, and it now has an overwrite function. So if you'll see, here's the actual PDF rendering of the before and the after, and you'll see how the allow overwrite parameter was added, the third parameter now. So all they would have to do now would be document or translate the one row and the one sentence that talks about allow overwrite. So here we are that's the way it looks in DocBook. So that's our XML. The green is all the new stuff. That's all that would need to be translated, and that shows on the other side. It shows in yellow what's been added. So, what else do we have to do to prepare our repository? Well, we had our repository laid out where it was the platform, and then there was documentation, and that's all it was. There was only one version of the documentation. It was in English. So now we have to put it somewhere. So we reorganizing using the IETF, which is the Internet Engineering Task Force, using their tags to support languages. So EN-US is English, the US version of English. And the first one that we're doing is for Brazil. It's for the project you saw earlier today. They talked about the Brazilian Credit Bureau. And so it's Portuguese, Brazilian version of Portuguese, so PT-BR. And later we might be able to do Mandarin Chinese, et cetera, et cetera. So we chose to use a two-part code rather than just the two-letter code because we might have variations, particularly with Portuguese. The Portuguese that they speak in Brazil is very different than what they speak in Portugal. If we were to ever have a Portugal version, it would be very different. So the subcode shows the national variety. And what I can't wait for is I want to be able to write code in Australian English and be able to say, "Good day, mate." So here we have our Git repository. So there's the folder structure of what we have for various languages. So we also realize that since we have different versions of languages, when we produce the PDF files, we're going to have to have naming convention. We're going to have to name them so that they include the language tag. So we added in our Jenkins build in our CMake files. We added that doclang. You'll see that highlighted in maroon there, and that gets expanded to the EN-US when we build the English version, PT-BR for the Portuguese Brazilian. So there it is. That's a list of our files that we produce in English with the doclang tag inserted in the middle of the file name. So what else? We discovered that we had a lot of common elements that are never going to need to be translated. The HPCC Systems logo, our little icons that we use in ECL Watch or in the IDE, they're never going to have to change. So those type of things will stay the same. So we're putting those in a common area where the other images, such as screenshots, each language has their own images folder so that the images can be translated as well. Then we had some not so common elements. One of the things that we had, our ECL language reference, was released under a different license than everything else. It was released under Creative Commons. So at the time when we first released it, the legal department said, just take the full Creative Commons license and put it in the book. Well, that's several pages. I think it's about 6 pages. Now, naturally, That's a legal document. We really, and it's one that we don't even own. We don't own the Creative Commons license. So when we had to go and translate this into Portuguese, we didn't want to take on the responsibility of translating that legal language. So we went back to legal and said, look, let's just put a link to the Creative Commons, and it goes to whatever language they're talking about. And so now in the English version of the ECL language reference, it points to the English version of the Creative Commons license, and in Brazil, they will see the one that has been approved by the Creative Commons people, and it's in Portuguese. So here's a screenshot of the ECL watch in Portuguese as well. That's one of the not common elements that needs to be translated. So in the English version of the books, they will have the English screenshots, and in the Portuguese version of the books, they will actually have Portuguese, because ECL Watch is one of the components in our application suite that contains the ability to be internationalized. And it depending on the locale where you're viewing ECL Watch, it'll translate it into various languages, and I think we support more than a dozen languages now. So in discussing with the translation company, they said, oh, this is great. We like the idea of only translating the deltas, and we can work fine with XML files, but how are you denoting your do not translate tags? Which immediately put me into a panic. What's a do not translate tag? Well, a do not translate tag is a wrapper that you put around a word or a sentence or a paragraph or a page of something you want left alone. Particularly with the ECL language, you obviously can't translate ECL keywords into another language. It wouldn't work. Our compiler doesn't do that. So the perfect example is the word join. Is translatable. There's a word in Portuguese for join. I believe it's juntar. I apologize for my pronunciation. But you wouldn't want to translate the word when it's being used in the context of an ECL language. So if you're talking about, you might want to say, use the join function to join two files. You would say that as use the join function to juntar two files, but you'd translate all the other words as well. I don't speak Portuguese. So how are we going to get these do not translate tags in? We were talking about it, and they really wanted them, and suddenly we were in a team meeting, and all of us were in there, and a voice from the back of the room said, "I have a tool for that," and that was David DeHilster, who's in the room right here, and he had a wonderful tool called Natural Language NLP++. So it's Natural Language Parsing ++, and it's a full tool. It looks like this. And with that tool, we managed, with probably about 7 hours of David's coding and a couple of hours of my testing and making more feature requests, we managed to churn through 3,000 pages of documentation and add the do not translate tags to 575 files in about 11 minutes. So it's great. So it's repeatable. We add the tags, send it off to the translator, and when we want to translate later, we'll just do the same thing with the delta files. So here's an example of the do not translate tags. You'll see them they're highlighted in maroon, and so in this particular case, we didn't want to. We had field names that were in the ECL code. We couldn't translate those field names, even though they were words that were translatable, because then it would break the code. So here's what it looks like in our XML editor, and you'll see that all the yellow things are the comments. Those are they're in the form of XML comment tags. So we can't leave them in there. We originally had thought that we were going to just add the do not translate tags and leave them in forever and just work around them, but it becomes too hard to edit the files with that many comments in the text. So one of the other things with this whole project, there were a lot of beneficial side effects. When we ran our 575 files or 3,000 pages of documentation through NLP++, there were some things that it complained about. So we found a whole bunch of special characters had been introduced 8 years ago during our initial import when we imported from Word and PageMaker, where some of our documents were forms. There were hyphen had been converted into EM dashes. Dot had been converted into the ellipsis character, which is an extended character. Smart quotes aren't really so smart, and Word always wants to change quotes, plain quotes into smart quotes. So in total, we found 1,450 errors that have been introduced by autocorrect. Now, unfortunately, the man who invented autocorrect has died, and he will restaurant in peace. We also learned that we needed more code reuse. We've always been big on writing modules that we could reuse in different documents so that if it ever changed, we would just fix it once and it would cascade through everything. So we found it even more important with the translation. If there was content that was repeated, they would have to translate it twice, and that's an extra cost to the project. So it's easier to maintain in any language when you have modules that you include. It's way more efficient, and you can write it once and use as much as you want for free. Another side effect of this whole project is we improved our automated builds and started a new thing that does independent builds. So we treat documentation just like source code. It's part of the project. When we build the platform, we build all the documentation. And when we build, when we release 6.0 and 6.2 and 6.2.2 and documentation is built right along with it. So we're tightly coupled. But we like the ability now, and we've added the ability now, to do even more documentation releases than the platform. So if we build 6.4 or 7.0, which is coming out soon, and we want to update the documentation before 7.0.2 or .4 that's coming out, we now have the opportunity to do independent builds, so we can release documentation faster than the platform. We've included, or we will be including Brazil, the Portuguese versions into the automated build, and other languages can follow. But the independent doc builds will be able to build either English or Portuguese or both. Now you'll see here's a sample of a docbook file that has been translated, and you'll see the English on one side and Portuguese on the other, and I'm told it was very good. And here's what it looks like when it's rendered. And again, I'm told that it's very good. I know that it looks good. So what's next? Today, Brazil, tomorrow, the world. We've got the opportunity now. We're open source. Anybody that wants to take on a translation project now can. We have made it easier, so it's an easier point of entry. So we'll add more languages. We're going to add more books. Now, we had to come up with a process of how we're going to add more books, because we have, in Brazil, we have a documentation team there. They're writing documentation, fresh documentation that's specific only to their project, but they're also helping with our translations. They're verifying all of the translations that they came out with, and they're also going to do the translation of the deltas when they're small. When we add a new book, like we've just added a book on Spark for the HPCC Spark integration, and WSSQL which used to be a third-party project, is now incorporated into the core platform, so it's a new book as well. Those two books will probably be sent to a translator. We're going to work that out with the team in Brazil. And then the other thing we plan on doing is creating CHM files. Those are compiled HTML files, which is what we use for the help file in the ECL IDE. If we can, right now we only produce those in English, but if we can build those in Portuguese, they can install that into their IDE, and when they hit F1 on a keyword, they will get a Portuguese version of the help file. The other thing that's left to do, there's screenshots. I showed you the one from ECL Watch. Right now, the screenshots are all in English, but ECL Watch is the only thing that's internationalized and would need translation. So they're going to start working on those. They just have to open the new ECL Watch and take the same screenshots that we've done, and by reading the manual, they should be able to navigate into those screenshots and recreate those in the Portuguese version of ECL Watch quite easily. And then we want to further engage the open source community. That's why we've made it easy to translate so that more people can contribute. And in conclusion, it's a small, small world. Now, that's the end of my talk about translation. Now, I do have a shameless plug. A couple of years ago, I made a presentation about the HPCC Systems Cookbook, which was a new thing that we were going to add. Unfortunately, I had some medical problems, so I didn't get to start it then, but I'm restarting it now. So I'm starting this project up fresh. And what it is, it's a way that the community can contribute to documentation. So a lot of people have expressed they want to contribute to documentation, but there's always a brick wall. There's always something in the way. You know, what if my idea isn't good enough? Well, somebody once said in a meeting, hey, let's make a movie about a tornado full of sharks. And there it is. Now I think we're at Sharknado 8. It's been a very successful franchise of very bad movies that are a lot of fun. So what are the other things that are still? Well, I don't know DocBook XML. I don't know how to write documentation in XML. I don't know how to use Git or do a pull request. Well, let me present to you the HPCC Cookbook. So what is the HPCC Cookbook? It's a collection of recipes and tips written by the best chefs in town, you guys. We'll have different sections. There'll be a lot of things on ECL. We've already got a couple submissions. Somebody has submitted one on how to do a phonetic search, how to use super files, super keys, and consolidate them periodically, how to modify a job name in a work unit, how to specify a work unit scope if you're into work unit scope security, and then there'll be some tips and tricks and techniques, how to use Git within the ECL IDE. It's integrated and just needs a few simple steps to use that. Some system admin how-tos, and the list just goes on. So I have an idea, but I don't know how to flesh it out. That's another brick wall that people have asked about. Well, or I'm not that good at writing. Well, you don't have to be, because we have a wiki. What you can do is there's 3 ways to contribute into the wiki. You can write directly in the wiki if you're comfortable with your writing and with your knowledge, and of course then we would look it over, and or you can write it and then say, I don't want to publish this yet, give me some pointers. And one of the good things about that is you get to write, and then you get the benefit of working with very experienced editors. There are 4 people that are editors for this. 3 of them are in this room, and one other one is not here today. But between us, we have close to 100 years of documentation experience.
Easily.
So if you don't want to write it, you could just send us an idea. Sometimes a question is very easy to turn into an article. Or you can just point us in the right direction. Show us a forum question that you found interesting that maybe already has an answer. Or you could submit a code sample that you've seen from one of your colleagues. Get permission first, and don't submit anything that's proprietary or intellectual property. But quite often you'll find some code snippets being shared among your ECL programmers on your team. Now, why should I contribute? Well, fame, fortune, of course. Well, not so much fortune, but you can get a little bit of fame. You get to work with professional editors, like I said, and you'll also be contributing and helping the community, and a contest. I don't exactly know what the prizes will be, but I've been promised that there'll be some, and we're going to look over the submissions over the next year and announce the winners at the next HPCC Community Day. And that's my time. So we have time for questions.
We do have time for questions. Any questions? Oh, all right. Let's start with the back of the room.
Thank you. So you mentioned the translation actually done by a translation company.
Yes.
Do they have any technical background in terms of translating a very technical document associated with HPCC?
Yes, it's true that they're translating very technical documentation. That's why it gets code reviewed by our
Native speaker?
Our native speakers.
Okay.
We have quite a few in the company that are on the Brazilian project and not on the Brazilian project that speak Portuguese. So they'll be verifying that. But yes, it's a technical translation company, so they do have some or quite a bit of technical knowledge. They're also very familiar with XML because it's very important that they maintain the XML integrity and not change any of the tags.
Great.
And not translate anything within an XML tag. For example, one of the things inside of an XML tag is an ID, and they can't change those IDs because those are used for includes and for reference points to do a see also creates a hyperlink type of thing.
Perfect. Yeah. Also, I heard that for the Delta, the plan was use the in-country team, which is the
Yes.
Brazilian has a technical writing person.
Yes,
or?
they do. They have
Okay.
they have a team actually.
They're
very good.
Okay, they have a technical writing. So, as part of release, right? Was that tied to as the like 7.0 or 7.x release document, or it will be a separate release document?
That's exactly why we need to have independent builds, is because there's obviously going to be some lag time. In English, we don't always finish everything on time because there's a smaller number of technical writers than there are programmers. So we're kind of outnumbered 10 to 1 right now. So we can't write as fast as they can code.
Okay.
So quite often we are delayed. The translatable ones will be delayed even further because they won't get the deltas until later. So that's why we're doing independent
Last question,
builds.
Richard. Last question. So documentation for the different language, it will tie back to the HPCC system website, or it will tie to the GitHub?
Well, all of the source code will be in GitHub. The produced manuals, the PDFs, and some in HTML format will be released to the HPCC Systems portal. So those will all be publicly available.
Great. And another question.
Lois, I think I have one.
First of all, is the translation done, and if so, how long did that take, that part, with the no tags, no translate tag?
The translation was actually finalized on Friday. I just found that out. So it is done to a point. Like I said, if you saw the to-do list, there are a few things that we still need to do, and there's 2 manuals that haven't been initiated because we've just added them to the documentation set. So how long did it take? We sent the files with the do not translate tags around February, and then it came back from the translation company. There were a few iterations back and forth with the translation company. The first samples that they sent were perfect. The second sample set had some issues where they had actually mangled a few of the XML tags. It seemed major at the time, but it actually was pretty minor. Once we told them what they needed to fix, they fixed it right away. So there was no problem.
Okay, any other questions? All right, I'd like to thank everybody for being here live and in the room, and those of you that are live streaming. We want to make sure that everybody is aware that these live stream videos are being recorded, and they are going to be available on YouTube for everybody. And for those of us that are in person here, there are going to be refreshments in the pre-function area right outside there. So thank you very much, and thank you for joining us in live stream. And we are done. Thank you.
Thank you.